In this video we're going to introduce linear functions, and I'm going to start by just showing you an image of a spreadsheet program, so Microsoft Excel. And you might have noticed that where we put in the formula to make this spreadsheet do some work for us, there's a little symbol here called f of x. Okay, so if I just highlight that, I'm talking about this area here. So we've got an f followed by an x, and normally what we would do is write this like this: f brackets x, and we refer to it as f of x. Okay, so what does that mean and what work is it doing exactly? Let's have a look. Okay. So what I'm going to do is write f of x equals, and we'll just use a very simple expression that we've looked at in previous set of videos, something like x plus 3. And we explained that, you know, we might think about this in terms of a shopkeeper who wants to put all of his prices into a spreadsheet and add 3 every time. So there's a £3 markup on every price. What we're doing now is we're saying, well, okay, this is a function of x. This is actually doing some work. So f of x simply means a function of x. And to look at this function in a little bit more detail, we're going to actually plot a graph. So over here, what I'm going to do is draw 2 axes. On the horizontal axis here, we're going to mark this x, so these are all our x values, and on the vertical axis we're calling this the y-axis. And so each time we have an x value, we're going to find out what its y value is and then work out what its coordinates are. So let's just number the axes. So we've got 1, let's just put some marks in here like this. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay, and up here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now I didn't have to number those in that way. I could have gone 2, 4, 6, 8, for example, but just for the moment, that gives us a very clear 10 by 10 grid of where we can mark our points. So let's see how we plot this. If we look at this function x plus 3, we can do a little table. So x and y. And what we'll do is say, well, what would happen if x is 0? Okay, put it into the function. 0 plus 3 will give us a y value of 3. And so we have 0 here, and the y value then is going to be here, 0, 3. So that's the first point. Let's do a few more. What if we just go, let's say 2, 4, 6, and 8, and then plug these values into our function. So 2 into x plus 3 gives us 2 plus 3, y equals 5. 4 plus 3, y equals 7. 6 plus 3, y equals 9. And now 8 plus 3, y equals 11. Okay, so now if we plot these other points, we have 2, 5, so 2, 5 here. We have 4, 7, so 4, 7. 6, 9, so 6, 9's up here. And then 8, 11, well, that's going to take us off our numbering here, but it would take us up to here. Okay, let's just correct that a little. There we go. Now this is if we've got separate points that we're plotting on the graph. But if we go back to our shopkeeper example, if this x can be any value whatsoever, so it might not be a whole number, for example, it might be a whole number and a fraction or just a fraction, then what we've got here is known as a continuous variable. The continuous variable. Oops. And all that means is that x can be any number in between these values. So for example, x could be 1.6. Let's let x equal 1.6. If x equals 1.6, then y must be 1.6 plus 3 equals 4.6. Okay? So in other words, when x is 1.6 here, roughly, okay, then we go up here and we would find 4.6, which must be roughly here. Now you can see what's going on here. If I kept doing this for the whole afternoon, then what would happen is eventually these will join together to form a line. And so we can draw that line for a continuous variable on our graph now, where our line, let's just erase this mark up here. Our line now represents any value that we put into x will come out with this value of y, and so we can plot anywhere along this point and read off what the x or the y value will be. For example, if I read along here to 6 and go up here, then I get 9. But if I wanted to find out something in between, say 5, I read up here and find out that my y value will be 8. Or if I went to 3.5, then I can read off the graph here that my y value is 6.5. So these graphs are really useful because they can show us visually what this function is doing, and they can be used to input any value and come out with any x value and come out with a y. Okay, so let's now try another function. Let's call this g of x. Okay, so just g of x now equals, well, let's have 2x plus 1. So if it's 2x plus 1, let's try our x and y values. We'll again go 0, 2, 4, 6 and 8. Our y values then will come out as, well, 2 times 0 is 0, plus 1 gives us 1. Plug in our 2 for our value of x, so 2 times 2 plus 1 will give us 5. Now we plug in 4. 2 times 4 is 8, plus 1 gives us 9. 2 times 6 gives us 12, plus 1, 13. And, well, let's not go too high because we're going to go off the end of our graph here. So there we go. But you get the idea. So now if we plot these on our graph, let's change the colour of our pen actually. Okay, so we'll use an orange, I think. Let's make it a bit darker. Okay, so now we've got 0, 1 would be here. 2, 5 would take us to here, so we're going to cross over this line here, this function here, and we've got 4, 9, which would take us to here, and 6, 13, well, that will be 1, 2, 3, that will take us off the chart, so it's going to be up here somewhere. But we've got enough. I mean, 3 really should be enough because we know this is a linear function. We can draw our line. There we go. So again, because this is a continuous variable now, we can read off any other values that we want straight from the graph. So if we wanted to know what y was when x equals 3, then we go along to 3, up here y equals 7. And that makes sense because 2 times 3 plus 1 equals 7. Finally then, let's plot another, let's change back I think to the blue. So let's plot another function. Let's see, h of x equals, now this time what I'm going to do is a fraction, half of x plus 2. Okay? And if I do that and plug in my x values, well, if I have naught, what will y equal? Half of nothing, half of 0 is just 0, plus 2 gives us 2. 2, 4, 6, 8. Okay. Now, if x equals 2, 2 times a half will give us 1, plus 2 gives us 3. Now 4 times a half will give us 2, plus 2 gives us 4. 6 times a half, half of 6 is 3, plus 2 gives us 8. Now, let's try that again, sorry about that mistake. Half of 6 is 3, plus 2 gives us 5. And the reason I realized my mistake here is because I can see a pattern. We always in maths want to look at patterns. Let's just round that y a little bit. Here we have 2, 3, 4, 5, so that we've got consecutive numbers. So I was expecting that to be a 5. So as soon as it came out wrongly, I knew I'd made a mistake. Good, we learn from our mistakes. So let's move on. 8 divided by 2, in other words, a half of 8 is 4, plus 2 gives us 6. And now plotting these on our graph. When x is 0, y is 2. Let's change the ink color again. Okay, there we go. When x is 2, y equals 3. Okay. When x is 4, y equals 4. Okay. When x equals 6, y equals 5, so we go up to here. And again, you can see that we don't really need to go on, but I will just do the final value. So 8 and 6, so 8 and 6. And then if we join these together, we've got a nice straight line going through all of those points. But again, we can say, well, what happens when x is 7? When x is 7, y equals 5.5. When x is 2.5, y equals 3.25. And let's just check that we've got that right. So when y equals 2.5, that's here. Let's just mark that with our pen. So when y equals 2.5, x equals 3.25, we're saying. So that's here, 3.25. Let's just check that. Get back to our blue pen here. So when y equals, when x equals 2.5, y equals, well, so we plug that into our function, h of x. We should write that over here actually, so that would make it much clearer, wouldn't it? Let's just erase that. So we're now working with our h function here. So y, sorry, making a few mistakes today, but never mind. Okay. So x equals 2.5 gives us y equals, well, okay, let's erase that. There we go. 2.5. Y equals, well, half of 2.5 will be 1.25 plus 2 will give us 3.25. So 3.25, which is exactly what we thought we would get. That is the value here. Okay, so that must be correct. So that's all we need to do for the moment. But I think that there's a couple of things that we could say about this. The first is that we started with something called a function. The function of x was x plus 3, that we were adding 3 to x each time. When we change the function, added a new function, we simply change the letter to make it g of x. That's also a function, but it's just a new function of x. And then we had a function of x here, which we called h. So we simply changed the letter, just advancing the alphabet, so that we make it clear that these are separate functions that we're working with. The other thing that might be worth pointing out is that when we change the coefficient of x, we change the angle, the slope, if you like, how steep the angle was that the line was drawn at. So, for example, here we had, let's just get our pen back. We had, well, let's just change the colour and you can see simply a coefficient of x of 1. And when we had a coefficient of 1, so we just had 1x, then if we look at our blue function here, you can see that it goes along 1 and up 1. It goes along 1 and up 1, or along 2 and up 2. In other words, it goes up as many units as it goes along. So that's what happens when we've got a coefficient of 1. When we've got a coefficient of 2, the interesting thing is this makes it twice as steep, as it were. So if we look at our orange line, we go along 1 here and now up 2 times 1, in other words up 2, 1, 2. Or if we went along 2, 1, 2, double the 2, 1, 2, 3, 4. So what this seems to do, this coefficient of x, is it gives us our steepness. Okay, it multiplies by 1. So that when we had a coefficient of a half, then it multiplied the x. If it was 1, it would multiply the x to only go up a half. So if we had 1 with this yellow line here, we went up by a half. If we had 2, of course it would be half of 2, we go up by 1. So the coefficient of x gives us our steepness, and if it's a fraction, then it's going to be less than a 45-degree angle. And if it's a number larger than 1, then it's going to give us an angle that's more than 45 degrees. So that's the first thing to look at. The second thing that I want to point out is where it intersects with the y-axis. This gives us our constant here at the end. So again, if we look at this blue line, the intersection with the y-axis here occurs at 3. So y equals 3. And here we've got in our function plus 3. So 3, the constant here at the end of our expression, gives us the intersection with the y-axis. And that's going to be something useful when we do more advanced mathematics. Here then, for our g function, we've got a constant of 1, so we would expect that to intersect with the y-axis at plus 1. So this was our orange line, and sure enough, there it is intersecting the y-axis at plus 1. Finally, we've got our h function here, which is represented by the yellow line, and again, if we look at our constant here, then that gives us our y intersection, and here it is at y equals 2. So two things to point out here. First of all, that let's just use a different colour here, that our coefficient of x gives us how steep the line is, so that gives us an idea of what the slope's going to look like, and our constant here gives us the intersection with the y-axis. And both of these are useful things to be aware of, because when we draw our graph, if we want to check, we can go back to see where it should have intersected here, so +3, and we can see that it should have been a 45-degree angle because of the coefficient of 1, and again we can see that that's a 45-degree angle. Okay, so I hope that's helpful, but in part 2 what we'll do is look in more detail at what is meant exactly by a function. Okay, so here we've got, well, I'm just using an algebra tile here, just a length or a weight, if you like, representing any value whatsoever. So we can call this x. And up to now, what we've been saying is that something like this simply represents any value that we want to put into it. If we introduce a second value, though, which we can call y, so we'll put y over here, and introduced an equal sign in the middle here, then this y value here must depend exactly on the x. So whatever x is, y has to be the same. So if we write this up here, our function of x at the moment, what x does is just reproduce, it copies exactly whatever we put into it and produces y, like this. So y must equal x. And there we go, we've just got a copy of x on our y side of the equation. Now what we're going to do is create make our function a little bit more complicated simply by adding 3. So our function of x, which we call f of x, is going to be x plus 3. Let's just erase these. Okay. So x plus 3, whatever value we put into this expression here, will come out as a new value of y. So y now is going to be 3 more than x. Okay, so y equals x plus 3. Now if we change the function, so change the notation to g of x, y seems to be exactly the same. It's still called y, but of course something's happened to it. What's happened to it? Well, it's changed. The function has changed. We now have 2x plus 1. So whatever happens to x, whatever x value we put in here, we double it and add 1 to give us our output y. And y depends exactly, again, just like before, on whatever we put into the expression over here. So here we've got, if you like, the work that expression is doing, and here we've got the output here. The value that we put into it, let's represent it like this. So that might be 3, for example. Goes into our term here, so 3 gets doubled, because x equals 3. So x equals 3, plus another 3, 6, plus 1 gives us 7, and so 7 is our output. Our output, y equals 7. If x was, let's see, if x was 4, what would happen then? Let's just erase this 7. If x equals 4, then x is 4, plus 4 gives us 8, plus 1, 9, therefore y equals 9. Now the idea of this is similar to the idea of computer programming. Sometimes this is called a function machine. But the important idea, the idea that I want to stress here, is that in this case x can be any value at all. So in this part of the function, the value that we can put in is anything. So x represents any value that we want to plug into it. Something very different with the y variable, though, is going on, in that y can't be any value at all. Y is a dependent variable. It depends entirely on whatever's going on over here. So we've got a new idea. Y isn't any value whatsoever. Y is a dependent variable. What makes it dependent? Well, exactly. What makes it dependent is this equal sign over here. Okay? So it makes it exactly dependent, not even roughly, exactly dependent on whatever the expression is over here because of this equality. So the equal sign tells us that there is an equality between both sides of this equation. And so if we look at our final function, let's have a look. Here we go. So now what we've got is h of x, and we're now using, our function is now y equals half x plus 2. So what we've done is halved our x and adding 2. So this time if we input 4 into our expression here, then we've got half of 4 giving us 2. 2 plus 2 gives us 4, so y is 4. Y has to be 4 because it's entirely dependent on this side of the function, on the h of x. So the idea of a dependent variable is a new one that we haven't looked at so far in these videos, and it's when we introduce a second variable, the other side of an equal sign, which gives us our dependent variable, dependent entirely on the expression on the other side. Now, if that expression only has powers of x and a constant, then we will always get, when we plot this, we will always get a line, a straight line, as we've seen in the first part of the video. So therefore, we say functions of this form that only have an x term, a constant, and the constant might be 0, so it might not be there, but there's a constant. So when it's in this form with an x term and a constant, and again any coefficient of x, then we will always get a straight line. So we call this a linear function. A linear function simply because it will always produce a straight line.